All right, let's just dive right into this. Welcome to today's Explainer, where we're going to unpack a really critical concept in plant and mechanical engineering. Specifically, we're focusing entirely on Section 3.3.2, Design Temperature. Now, even if you're a total beginner stepping into the world of industrial design, this is a principle you absolutely have to wrap your head around. I want you to imagine a massive, multi-story steel tank holding thousands of gallons of highly pressurized, volatile liquid. We aren't just talking about making sure a pipe doesn't spring a tiny leak here. We're talking about preventing catastrophic industrial disasters. The core principle keeping that beast safely contained is what we call design temperature. It acts like an invisible shield, dictating not just the physical safety of these giant pressure vessels, but also the immense legal liability of the engineers who build them.
So, before we get bogged down in all the complex math and rigid engineering codes, we really have to start with a fundamental, real-world question. What actually happens to solid metal when a massive industrial machine is pushed past its thermal limits? We aren't just talking about accidentally leaving your kitchen oven on for too long. We are talking about towering pressure vessels holding incredibly volatile chemicals. When that heavy steel gets too hot, it undergoes fundamental structural changes, so the stakes for getting this right are frankly monumental. To really get this, we need to separate two key terms. Think of operating temperature as the speed you normally drive your car on the highway, say 65 miles per hour. It's calm, predictable, just expected daily use. Design temperature, on the other hand, that's the absolute maximum speed the car's frame is built to survive. It's like driving it at 200 miles per hour into a wind tunnel just to see the exact moment the frame begins to violently shear apart. In plant engineering, almost all of our safety and strength calculations completely ignore that calm highway cruise. We focus entirely on that absolute safety ceiling.
By definition, the design temperature is a strict, uncompromising guarantee. It dictates that even if the internal chemical reactions run dangerously hot right up to this exact precise temperature, the equipment will survive with literally zero mechanical problems. It is the ultimate line drawn in the sand by engineers, because if a facility crosses that line, a catastrophic rupture isn't just a cracked valve. It could mean a localized explosion, massive toxic chemical spills, and immediate fatal danger to everyone on the site.
Now here's where it gets really interesting. This single temperature value creates a high-stakes legal divide in heavy industry. It basically acts as the ultimate blame game. If a machine breaks down or structurally fails while running below the designated design temperature, the engineering company or the vendor is entirely at fault. They simply didn't build it strong enough, and they're going to pay millions in damages. But if the plant owner operates the facility poorly, pushes the equipment above that design temperature, and it breaks, suddenly the engineering company is legally shielded. It becomes entirely the owner's fault for operating it dangerously.
So, knowing the immense financial and legal liability tied to this exact number, how do process engineers actually decide how much higher the design temperature should be compared to normal everyday operations? You can't just pull a number out of thin air, right? And you definitely can't just pick a temperature that intuitively feels safe. You need a rigorous standard that holds up both in a court of law and out there in the field.
And that brings us to the global standards. A perfect example of this is the Shell Design and Engineering Practice, or Shell DEP. Now, this isn't just some random corporate memo. It is a rigorously tested benchmark respected and used by process engineers all over the globe. For normal services, it gives us a really strict rule of thumb. You must always take your normal operating temperature and add a minimum 10 degrees Celsius safety margin to establish your official design temperature.
That 10-degree buffer is incredibly crucial. It acts as your primary safety net, because in real-world chemical processes, temperatures simply don't stay perfectly flat all day. You have constant thermal expansion and contraction. You also have unexpected process anomalies, like, say, a sudden chemical reaction spike that flashes intense heat through the entire system in a matter of seconds. This buffer ensures that a slight operational hiccup doesn't immediately push the thick steel past its structural breaking point.
But let's pause and take a step back to ask a more fundamental physics question. Why are we so fiercely obsessed with just 10 degrees when calculating the mechanical strength of a massive pressure vessel? It seems like a tiny margin. Actually, it is a tiny margin for a giant metal tank. So why does a slight increase in temperature matter so profoundly to thick, solid steel?
This stress-strain curve we're looking at brilliantly illustrates the answer, and it's a foundational concept in mechanical engineering. Notice how at lower temperatures, represented by the blue arc, the metal graph reaches incredibly high. That means the steel can take a massive amount of physical stress before yielding. But as the heat rises inside that vessel, which you can see with the red line, that physical strength and ability to handle internal pressure dramatically plummets. The metal effectively becomes softer, stretching and weakening under the exact same physical load.
Because heat weakens metal in this highly predictable way, engineers rely on a concept called allowable stress. This is the absolute maximum physical load that a specific material is legally and physically allowed to handle. And here is the core takeaway for any industrial design. Engineers must find the material's allowable stress based strictly on the higher design temperature. They never, ever base it just on normal operating conditions.
To find this exact legally binding strength limit, engineers consult what is basically their industry Bible, the ASME code tables, specifically Section 2, Part D. This massive, meticulously calculated grid of numbers acts as the definitive guide. It shows exactly how the allowable stress of very specific metals drops off a cliff as the environment gets hotter and hotter.
Let's look at a practical example directly from those tables to make this concrete. Imagine we're building a vessel using a standard stainless steel plate, specifically SA240-304L. If our calculated design temperature is 200 degrees Celsius, we follow the table and find an allowable stress of 110 megapascals. Just to visualize what that actually means in the real world, a tiny 1 centimeter by 1 centimeter square bar of this specific steel could safely suspend about 1 ton of weight, even while baking at 200 degrees. Pretty wild, right?
But here's where the math gets really unforgiving. What happens to our structural integrity if the process engineer reviews the system and decides to increase the design temperature by just a single degree, moving it from 200 up to 201 degrees Celsius? I mean, it's just one tiny degree on a massive industrial scale, right? Does it really matter?
Well, yes, because the ASME tables are incredibly rigid. They jump in strict set increments. There is no middle ground, and there is no column for 201 degrees. Passing that 200-degree threshold forces you to jump straight to the next column up, which is a massive leap to 250 degrees. In the blink of an eye, your legally allowable stress drops from 110 straight down to 103 megapascals.
So, the absolutely crucial point here is understanding the domino effect of that single degree. That sudden 7% drop in your material's allowed strength means your original design is now legally unsafe. You can't use the same thickness of steel anymore. You have to upgrade to thicker metal plates just to compensate for the weaker state of the hot metal. And thicker plates mean heavier equipment, drastically higher material costs, and massively increased fabrication time. Literally, 1 degree can heavily drive up the financial cost of an entire multi-million-dollar project.
When we zoom out, we can see how this whole process follows a really strict, logical life cycle. First, you carefully identify the normal operating heat of your chemical process. Second, you add your critical safety margin, like that globally recognized Shell 10-degree rule we talked about. Third, you definitively lock in that design temperature. Fourth, you consult the rigid ASME tables to find your weakened allowable stress limit. And only then, after all those variables are legally secured, can you actually design the structural thickness of the machine itself.
Ultimately, selecting the design temperature is the ultimate engineering balancing act. Make it too low, and you risk a catastrophic facility failure and massive legal liability. Make it too high, and you bankrupt the project by paying for overly thick steel that you didn't actually need in the first place. It leaves us with a fascinating challenge. In a world full of volatile variables, how much safety margin is truly enough to protect your facility without bankrupting it? Thanks for exploring the invisible shield of design temperature with me today. See you next time.